Okay, so now we want to do problem 9. I'm sorry, problem 10 from chapter 9. A thousand automobile is a rest at the traffic signal. So that's we call that M1. So M1 has a mass that's 1,000 kilogram, and it is initially a rest. So that's initial V1I. Initially, it has 0 velocity. At the instant the light turns green, the automobile starts to move with a constant acceleration that's 4 meters per second. So A1 has acceleration, and that's 4 meters per second square. At the same instance, a 2,000 kilogram truck traveling at a constant speed of 8 meters per second overtakes and passes the automobile. So that's M2, the truck, has mass that's 2,000 kilograms. And the velocity is a constant, so that's V2 that maintained at 8 meters per second. So we're asked to find how far is the central mass of the automobile truck system from the traffic light when t equals to 3 seconds. So at time equal to 3 seconds, where is COM? Okay, and also what is the speed of the CO then? So in other words, you want to find the position, center mass, the position of center mass, and also you want to find the velocity of center mass. Okay, so we can draw this diagram like this. So you have M1, this is automobile, and this is the truck, and they are moving in this rightward direction. Okay, and the second truck overtakes the first one. So you can see that at t equal to 3, M1 will have traveled at this position, and M2 will be located at this position. And you're asked to find where is the central mass. Okay, so how do we do that? We just basically, start from the definition. What is the definition of COM for position? So if you remember, that's basically equal to the position of the first one times the mass of the first one plus the position of x2 and then m2 over the combined mass, m1 plus m2. So let's say this is your x1 and this is your x2. So this is how you calculate the central mass. Okay, so m1 and both masses are given. So we need to figure out what is x1 and what is x2. So based on the equations of motion, you have initial velocity that's 0, you have the acceleration that's 4 meters per second square, and you have time that's 3 seconds, so you can easily calculate your x1. So what is your x1? Your x1 is equal to x initial position plus initial velocity times time, and then plus 1/2 at squared. So if we plug in, if your x0 here, we call that 0. So in that case, the first one does not have contribution, and initial velocity for car 1 is 0, so you don't have to worry about that. And then plus 1/2 the acceleration is given, and the time is also given. So you have the x1, which is 18 meters. So at time equal to 3 seconds, this is located at 18 meters. What about your x2? Now x2, because it's moving at a constant velocity, does not have the acceleration. So you can still use this equation. It's just that x2 now is equal to x0, and then plus the v2 times t, and no acceleration. So in that case, you have 0 here, and your v2 is 8, and your time is 3. So x2 will have moved to the position that is 24 meters. So we have all the information we need, so we just plug into this equation. So you have 18, and then times your m1, which is 1,000, and then plus your x2, which is 24, and then times the m2, which is 2,000, and the combined mass is 1,000 plus 2,000. And so after you plug in the numbers, your the central mass will be located at 22 meters. Okay, so that's the location of central mass. So that's an easy one. As you can see, basically we just use this definition of central mass, and then we calculate the position according to the equations of motion and plug into this equation. Then you get your answers. And then you also find what is the velocity of central mass. The velocity of central mass. So in order to do that, again, we're going to use the definition. So your VCOM is basically equal to m1 V1 plus M2 V2 over M1 plus M2. Okay, so the question is, what is V1? Because V1 initially has zero velocity, but then it has acceleration. So your V1, again, according to the equations of motion, your V1 is basically equal to initial velocity plus the acceleration times time. The acceleration is 4 and your time is 3, so it would have it would have reached the velocity that has a magnitude of 12 meters per second for the first car, and the second car, because it's moving at a constant speed, so the velocity does not change. So now we can just plug into this. So you have 1,000, and then times 12, and then plus 2,000 times 8, and over the combined mass, which is 3,000, so that the velocity of COM would just be 9.3 meter per second. This is like when you treat this two-car system, two-car as a system, and the center of mass would, will have the velocity that is 9.3 meter per second. Now, likewise, we can also calculate the acceleration of center of mass. So again, that would just be using the equation. So you have A1 M1 plus A2 M2, and then over the total mass. And as you can see, the A1 is 4, so you have 4 times 1,000, and then your the car 2 has no acceleration, so there's no contribution, and over the total mass. So you can see that just like this is the acceleration of the system. Okay, so you can see that all this are very straightforward just by the applications of the definition of center of mass. So that's your problem 10. Now we're going to do problem 12. Okay, so problem 12, let's see. Two skaters, one with a mass that's 65 kilograms and the other with mass of 40 kilograms, stand on the ice rink holding a pole of length that's 10 meters and negligible of mass. Starting from the ends of the pole, the skaters pull themselves along the pole until they meet. How far does the 40-kilometer skater move? Okay, so let's draw a diagram first. Let's say this is the first skater. The mass is 65 kilograms. And this is the second skater. And the mass is 40 kilograms. And you can see that this one has a smaller mass and this one has a larger mass. And they're connected by a pole. And they're trying to reach toward each other on a frictionless surface. So they're just going to walk toward each other. And you're asked to find how far is the second skater has to move until they meet. So let's say they meet somewhere here. And your task is to find position X here. Okay? So let me just say this is the meeting point. So we can define our coordinate to be that this, we take it to be 0, and this, we take it to be 10 meters, because that's how far that's the length of the rope. So in other words, this starts from the origin and moving rightward, and this starts from the end of the pole and moving leftward, and eventually they're going to meet at some point. So the question is, where is that point? Now this is an isolated system, so the center mass does not change. So in that case, how do we find the center mass? So basically, the center mass will stay the same. So when they reach each other, the central mass, that will be where the central mass is. Okay, so we can base on this diagram before they move toward each other to find out where the central mass is, and then set it equal to, when they both meet at this point. Okay, so in other words, the center of mass, by definition, will be equal to the x. Let's say this is x1 and this is your x2. So you have your x1 and then times n1 plus x2 times n2 over n1 plus n2. Okay, that just directly from the definition. So before they meet, you will have this value. So x1 is 0, and then x2, your x2 is 10, and your m2 is 40, and then over the m1 plus m2, so you have 65 and then plus 40. This is where the central mass should be located. Now, when they move toward this point, this is where the central mass would be. So what would that be? So let's say m1 has moved to this position. So this is m1, the position of m1, and this is where the position of m2. So you will have the x1. So that will be 10. Let's say this has moved. So let's say this has moved x position, and so then this will be 10 minus x. Okay, so you will have 10 minus x, and then times the combined mass, which is because they both meet at that point. So you have 65 and then plus 40, and then over the total mass of system. That will be 65 plus 40. So you can see that these two, they cancel each other. So what you have here on the right-hand side, you just have 10 minus x, okay? And that's equal to, you can calculate this numerical value. And the numerical value, that would be 3.8 meters. So this position is 3.8. So once you have 10 minus x. So you have 10 minus x, that's equal to 3.8. So in other words, how far would this the second scalar has to move? It has to move 10 minus 3.8, which is 6.2 meters. Okay. So this problem, basically utilize the definition of central mass. The central mass, when you have the initial scalar, when both masses are at both ends, you can calculate where the central mass is. And then once they come toward each other, then all the mass are contained at this point, and the position we can call this as x. If this is x, then this will be 10 minus x. So you have, in reference to the initial point, this is the distance. This is the distance where according to, from the origin and of the central mass. So that will be 10 minus x, and then times the total times the mass of the system, and then divided by the mass of the system, because both points are located both masses are located at that point. Okay, so once you say that, then your x here, after you do the calculation, your x is just 6.2 meters. Okay, so that's that. So the next one we want to do is problem 19. All right, let's see. 19. So a 21 kilogram truck traveling north at 41 kilometers per hour turns east and accelerates to 51 kilometers per hour. The mass of the truck is 2,100 kilograms, and it's traveling north. So I'm just going to draw a diagram. It's traveling north, and that velocity is 41 kilometers per hour, and then turns east, accelerates to the velocity, which is 51 kilometers per hour. Okay, and so you also find the change in the kinetic energy. So what is the change in kinetic energy? What is still okay? And then you also find the magnitude and directions of the change in momentum. So what is the directions and and the change in the momentum. So let's see. You have a car with this mass that's given, and it's moving northward, and then it's going to, and then you make a right turn and heading toward east with and accelerated. So the velocity changed from 41 to 51 kilometers per hour. The first thing we do is that we need to express this, change this units to SI units. So let's say this is your initial velocity. This is your final velocity, and what we also need to do is that we express these vectors in unit vector notation, so you have a better idea what's going on. For example, this car is moving northward, which means that it has a positive y component, but no horizontal component. And this one, after you make the turn and accelerates, it has no vertical component, but it has a horizontal component. Okay, so that VI is equal to 41, and I'm going kilometer per hour. So that's 41 times 1,000 over 3,600, and that will give you your V1. That will give you 11.38 meter per second. And I'm going to express that in unit vector notation because it is pointing upward. So the whole thing is j hat, and you have no I hat component. Okay. Now VF. So your VF is equal to 51 kilometers per hour. So that's 51 times 1,000 over 3,600. So your VF is equal to 14.17 meters per second. And I'm going to express that in unit vector notation because it's rightward. So you have I hat, but no j hat. Okay. So once you have this, once you have this, then the first thing you ask to find is that what is the change in kinetic energy? You're given the total velocity. Okay, so this VI, this is the 41 here is your velocity, the total velocity. So you can use the equation 1/2 mv squared to calculate the initial kinetic energy. And then this one also is given as total velocity, so you can use that to calculate 1/2 mv squared for the final kinetic energy, and then take the difference that will give you the change in kinetic energy. So let's do that. So you have delta K that should be equal to Kf minus Ki, and your Kf is just 1/2 mass of the system, 2100, and then times the velocity. So VF has this magnitude 14.17 squared, and then minus 1/2 2100, and then initial velocity 11.38 squared. So after you do the calculation, you should get the change in kinetic energy is 7.5, and then times 10 to the 4th joules. You can see that the change in kinetic energy is positive. That's because the object is accelerating and reach a higher velocity. Okay, so that's your part A, and then you're asked to find the change in momentum. How do we calculate the change in momentum? We know that momentum is defined as mass times velocity. So you have the initial linear momentum. You have the final linear momentum. So we can calculate the change in linear momentum. So in other words, your delta P. But then this one, delta P is actually a vector. So your delta P is basically final linear momentum vector minus initial linear momentum, and those should be in the vector form. So if you do that, and then this is just your VF minus MVI vectors. Okay, so you can see that we have VI that's only in the vertical direction. We have VF that's only in the horizontal direction. So what we have here is that you have 21, that's mass, and then times your VF. Your VF is 14.17, that's your I hat, plus 0 j hat, that's your MVF. And then minus 2100, and then times VI. Your VI is no I hat, but you have 11.38 j hat. Okay, so after you do the calculation, so you can see that what you have here now is you have your X and Y component. So your S component, you have, let's see, your S component, you'll have the 29 29757, 29757 I hat. And in a vertical component, that's negative. So minus 23898J hats. Okay? And the units, of course, is kilogram times the units of the velocity. So this is a change in linear momentum. Okay, so you have the x component, you have the y component. That's your part 2, but then the last part asks you to find out the magnitude of the linear momentum and also the direction. So how do we do that? So this is a vector. You have the x and y component. We use Pythagorean theorem to find out the magnitude. So your delta p will just be the px squared and then py squared. Okay, so you have this magnitude square, and then plus this magnitude square, and then take the square root of the sum, and you should get 3.8 times 10 to the 4th kilogram times meter per second. And that's the magnitude of the change of linear momentum. And you also find the direction. In order to find direction, again, I would, whenever you have a vector, you want to find direction, you want to plot it on the x and y coordinate to see which quadrant the vector is pointing. So let's draw that. So you have the x component that's positive, and you have the y component that's negative. So your vector, your delta p, is actually pointing that direction. So we can calculate this angle. If we use this angle, so then your tangent theta is equal to the y component. The y component, absolute value of y component, so that's 23898. And then over the horizontal component, the horizontal component is 29757. So after you do this, the angle that you calculated is 38.7 degrees. That refers to that. So in your answer, you might say that it is 38.7 degrees below the horizontal axis, or you can just say that it's negative 38.7 degrees. Okay, so that's